So good evening. I'm here to present my project about text-to-speech algorithms. I will be focusing on the Natural Speech 3 paper, which was written by Zutan, and it's one of the latest models that is trying to assess the shortcomings of the current text-to-speech models. However, my knowledge in text-to-speech is not that deep. I took a rather easy approach so as to go through implementing a TTS model locally. My main focus here would be using Glow TTS and Mozilla AI, or now recently renamed as Coqui AI. So I'm going to talk about understand the basic mechanism of TTS models. What is exactly Natural Speech 3 trying to address in terms of speech characteristics like timbre, pitch, frequency, etc. And then, because of the competition limitations, I choose to go with a simpler model. So I just went with Glow TTS. I'm going to go through how to train a model, how to train a vocoder, and implementing Tortoise and Glow TTS to generate audio. So let me start with basically exploring the Natural Speech 3 paper. So Natural Speech 3 was made with the Natural Speech 3. There was the paper I chose to gain some background in text to speech. I used this paper and backtracked it to Natural Speech, the first model where the main focus was to focus on the naturalness of the audio that has been created and to remove the robotic uh, kind of inputs that were there in the particular thing, in the particular model. So it is a cutting edge text to speech system that addresses the limitations of existing models in speech quality, similarity, and prosody. The main feature of this was that a neutral codec uh, was made with factorized vector quantization, and this allowed uh, the model to handle the different parts of speech, and with constant training and the increase in data, there were a lot of improvements in the performance. This model was specifically designed to address those nuances in the voice in the text to speech models that make this that make the model sound too robotic. So you cannot ask AI to like generate a song for you, or you cannot ask it to sing it in a particular way. So these are like some of the things that I noticed as part of like my exploration with this project. So moving on with the architecture of this particular model. So in the first layer that we see, the text goes through this model and goes through the phenome encoder, which basically the system takes the encoding of the text and breaks it down into specific units of sound, each alphabet or letter having their own sound. Duration diffusion, this is basically telling the model, trying to understand from the phenome encoding what is the duration of each phenome or how long each sound is going to take. Then comes prosody. This is basically where the rhythm, the speed, the basically the feeling behind that particular speech, or also known as intonation. Basically, it could be a happy, sad, or basically there's a speaker emotion attached to that. Then comes content diffusion. This is basically the actual content of the speech. This is where all the meaning is involved. Focus more on the subject, and the other parts is like, you know, ranking the sentence in a way you could say. But yeah. And detail diffusion. Detail diffusion is it adds to these particular subjects. There is more details involved, basically like breath sounds, like Sounds like lip smacks, something, basically something that makes your basically the things that human speech has when they're talking. They're like small things that you might not even notice, but yeah, it's there. So yeah, this is basically how the model was built, and over here WER stands for word error rate. As the training hours increased, the word error rate decreased, and here SIMO was used as the model evaluation. So yeah, so your speech would come, it would get encoded into a particular format, and these factorized diffusion would help basically understand like what exactly is the current tone or value, phenom, basic, your what your text to speech model does. It gets it in those particular formats, and then this timbre embedding is considered into this case. So basically in factor diffusion we add this timbre embedding so that we can get a more naturally sounding speech. And this is then passed to the coder decoder, and then we get a final speech. So natural speech uses LibriSpeech corpus for its training. It was trained for around 200,000 hours of data, and it scaled up to 1 billion parameters. However, for the course of this project, I decided to just take this as from a research point of view and kind of get an understanding of what exactly is happening, in one of the latest text-to-speech models. Uh, Talking a little more about the data set, LibriSpeech is a very clean data set. It had around 1,000 hours of 16 kilohertz read English speech. It had audiobooks. It was also sourced from the LibriVox project. Uh, Most of their models, the Natural Speech 2, Prompt TTS, all these belong to Microsoft Research in Asia. Uh, I tried reaching out to Mr. Zudan, but did not get that much response from him. Although I did learn that the GPU I had was not enough to run this model. Moving on. So this is the main place, like from a beginner's point of view, how to like implement TTS on your system locally. So this is where I came across Coqui's Glow TTS. And why I chose this was because it was easy to understand. It was beginner friendly. It had extremely good documentation. You could easily set this up on your system. It was able to access and explore multiple TTS models. So basically, this TTS would give us the chance to run many different inbuilt TTS models, or basically different techniques of TTS. Some of them would be the RNN approach, like Tacotron 3. Some of them would be GANs. Some of them would just be attention models. So multiple models were available in this particular package. So I chose this one. Easy integration with TTS datasets. What I did love about this is that it was pretty straightforward. It required all the WAV files to be in a folder and required a metadata.csv file to have the transcription of whatever was happening inside each of the WAV files. WAV files are your audio files. Basically, for training, we needed to provide these particular WAV files for the training. Let me just pull it up real quick so that I can show it to you. So this is what it is in TTS recipes LG speech. This is the one that I used, LG speech. Here are the WAV files. Here, these are the audio files, and this is the metadata. What exactly the metadata includes is the transcription of what exactly is happening in that particular WAV file. So if you see it properly over here, you could see that it's like a continuation of a sentence, maybe a gap. But yeah, this is basically a short introduction to what the dataset actually was. Moving on, setting it up. It was pretty straightforward. You do just have to pip install TTS, clone it from Git, and install the dataset. Though what I showed you earlier, this was the dataset. It has around 13,100 WAV files, and the metadata CSV is all the transcription for all this audio files. This is the training data that we'll be needing for our model. Yeah, this is the hardware that I used. I was using an NVIDIA 1650, and this was run locally on my system over here. It's not the best GPU, but this is the best I could do with or locally. I mean, I wanted to check how easily implementable it is. So yeah, this was a good start for me. A dataset config. This was the piece of code that I had to use to basically understand that this is the LJ speech thing that I'm going to be using. And this metadata, the meta file train, is basically where the subtitles are. What I do love about this is that you could easily use it for the different types of data set that there is. This is just a representation of what I was trying to show you earlier. So training the model. So the reason I chose Coqui Glow TTS is because it was originally known as Mozilla TTS. It was one of the leading open source projects that focused on text-to-speech technologies. It there are a lot of uses to it, especially in the terms of accessibility and user experience improvement. Uh, I chose to use Glow TTS. These were the parameters that were there in the training. For training, I this was the default parameters that I used. Obviously, epochs 100 was one of the things that the first thing that caught my attention. 1,000 epochs is a long time for any model to run. But it just so happens is what happens is that if I would set it less than this particular value, uh, it would it would not the attention would not build for that particular model, and sometimes it would not train well. So that's why I just kept it 1,000. However, I was able to train for 25 epochs, and I was able to get a decentish result where sometimes what would happen was if I would have given it some words that did not belong to this language, that model was not ready to understand something like some phrases in Hindi or Spanish or French. So there was something for me to explore, but given the complexity of that and given the time frame for this project, this was the best I could do. So basically, this is how the model was run. There were around 1,000 epochs, and this global step would probably just tell us the number of uh, audio files that have been gone through and basically how well the model is training. I'm sorry. So yeah, I have run it locally over here. Here you could see like this is the model training thing. Uh, it was this was actually run for 23 hours before this particular setup. So out of 13,000 in 23 hours, I was only able to achieve 33,550. Not the great performance, but what's the best thing about it is that on completing a particular number of steps, it gives us the best model. I don't know if you can see it, but it on every epoch, it gives us something like this. This is an actual runtime variable that I have here. Uh, so yeah, this is the evaluation performance. This is actually a comparison from the previous model. So if this is epoch 8, that means this is the evaluation results of epoch 7. And the good thing about it is that every time the one epoch gets completed, it saves the best model. So this is actually 3,248, which is a good number, no doubt. Okay, moving on. Moving on, after training the model, the main part of this model is basically understanding the need of a vocoder. Vocoder is something that is the process of generating speech is usually done in two stages. You convert the text into a spectrogram. Spectrogram is like a graph of sorts that probably is not understandable with the human eye, but it's understandable with the machine. And this spectrogram is then converted into a waveform. Waveform is what we understand. So basically, it contains all the audio information that we need. but it's not directly audible. So we have to still work on that. So the model often used is Tacotron 2 and fast speech for the vocoder training. And the benefits of using a vocoder model was it improved the quality of speech. You could focus on the characteristics of the speech. It could handle different voices, accents, speeds, etc. It was efficient. It would reduce the roboticity of the of this particular output, and it was robust. And yeah, this is basically it. This is what I completed my researching on. I also had the opportunity to use my trained model and vocoder to generate some text. So I do have something over here, output file generation. I'm going to give like a small little demo of what the server is, and yeah, that's pretty much it. Output file generation, basically all you had to do is go to the kernel, go to the console, just do tts dash dash text. I'm not sure whether you can see this part of the screen, but okay, I think you can see it. You say this is my home, welcome. Okay, that's all. That's all you need to do. You just hit enter. It takes a little bit of time for it to start. So yeah, just resuming my previous conversation. So yeah, this generated the particular output for this is my home and welcome. So I just need to go to this particular directory. All of this was done on Windows using WSL. And here in this directory, it generates a TTS output file. This is my home. Welcome. So the reason why you can hear it is still robotic is because the model was not trained fully. I had to like pull the plug on it some time back, and because of that, it's not been trained fully. But then it has still it has still given us decentest results. When you think about it, out of 1,000 epochs, you're pulling it out from the seventh and eighth epoch, and you're still getting like this result. It's pretty amazing. Also, I want to go through the TTS server. So basically, this is the front end part of it uh, that we can use to run the model on a page. All you have to do is probably type here, welcome to this page. This is a text to speech model. So you see over here.
Welcome to this page. This is a text-to-speech model.
You see, it was pretty smooth with whatever it had. It's using the same Hyphagon generator, Hyphagon discriminator combined with the Glow TTS to give us the output that we need. So yeah, that's pretty much it. You can have a look at my paper. I have a white paper ready for it, just in case we need to. You guys need to get any of the links. I have the output file. I have the input file. The references citations. Basically, the outcome of this project was pretty straightforward. I wanted to explore TTS models to understand how the flow is from a general. Basically, first I want to understand how a speech model is trained. What exactly do they see when they are training the data? Uh, when they're training a model. So basically, the whole architecture of natural speech was amazing. Although to implement it was another story. But yeah, seeing how to use a TTS model, understanding all the nuances, the different type of speech, different type of speech speechers. I don't know what it's called. Speakers. Yeah, sorry. Basically, a little bit of that. training the vocoder model, basically this was one of the most important things that I learned, that just training a model wasn't enough. You had to train a vocoder to make it more robust. Uh, but yeah, just talking about the ethical challenges, we all know that cloning or making text-to-speech models comes with it's a double-edged sword. It could be used for wrongdoings. But yeah, it is a bit difficult. Even when you're using the speaker data, the person's voice you're going to be using for training, you should have his consent for that. Uh, yeah, so all these things, there should be a set of rules and regulations that need to come along with this model, which is definitely an area of research for me at the moment. Uh, and that's it. Thank you.